So in today's session, we're going to do a review of reciprocal trig functions and how to enter them onto CAS. We're going to review their graphs and also think about how the behavior comes about. We're going to look at finding the asymptotes and the domains of reciprocal trig functions. And then also, once we do that, we're going to look at some inverse trig functions, ways that we can interpret them by both algebraically and geometrically, and then also review their graphs, and also importantly, finding the domain and range of inverse trig functions. And then throughout, we're going to look at some exam-style questions for both reciprocal and inverse trig functions. So, earlier on in the year, you may have come across three new friends, sec, cosec, and cot. So sec was 1 over cos, cosec is 1 over sine, and cot is 1 over tan. Now, in order to enter these guys into CAS, on the left-hand side of our CAS, there's this trig button here. So if we click that, we bring up the submenu with all of our trig functions. Now, just one thing to keep in mind, importantly, with cosec on the CAS, it's abbreviated as CSC. So whenever you see this in sort of CAS input or output, keep in mind that CSC is just shorthand for cosec, whereas sec and cot are normal as they are. Okay? So before we look at some graphing, just one thing to keep in mind. When we divide a number by a really small number, such as 0.1, we're going to get a bigger number, such as 10. And when we divide by an even smaller number, we get a really big number. And then opposite-wise, when we divide by a big number, we're going to get a small number. So just keep that in mind before we look at some graphs. Okay? So in methods and also in units 1, 2, we were sketching cos graphs, this red graph here. Now in Spec, we may have sketched some sec graphs previously. So this black graph here is our sec graph. So we need to think about how this graph actually comes about. So what we can do is we can think about our cos graph. Now cos, the range goes from -1 up to 1. So as cos is getting smaller and smaller, right, we're dividing by a smaller and smaller number with our sec graph. So we're going to get a bigger and bigger number. And it's reflected by the increase in this black graph here in our sec graph, right? So as cosine's getting smaller and smaller, our y value is getting smaller and smaller, sec is getting bigger and bigger. And then as we're about to hit pi over 2, right, we're going to divide by 0, which we're not allowed to do. And therefore, we're going to get this asymptote. Okay? And we can keep on going as we increase our x values. All right? X is now getting a little bit bigger and bigger. So that means the y values are getting smaller and smaller. And then when we approach 1, 1 over -1 will correspond to a y value of -1. All right? And then once again, as our y values are getting bigger and bigger, then 1 over those y values are getting, so as our y values are getting smaller, 1 over y values are getting bigger and bigger. And once again, as we're dividing by 0, we're going to pick up an asymptote there. Okay, we can repeat this behavior. So important thing to note with the sec graph, and likewise with cosec and cot, is we're going to pick up some asymptotes whenever cos, sine, or cot, or tan is going to be 0. Okay, so whenever our cosine, sine, or tan graph hits the x-axis, we're going to pick up some asymptotes there for our sec, cosec, or cot graph. Okay? And what's also to keep in mind is that they do occur periodically. So just like how the x-intercepts occur periodically, the same is true of our asymptotes. And also keep in mind that with our so the question was, do we write cosec in our working out? Preferably just write cosec. So with our graph, with our cos, we're getting a local maximum around our y-intercept at 0, 1. So that corresponds to a local minimum on our sec graph. So wherever we're picking up maximums on our cos, we're going to pick up local minimums on our sec graph, and vice versa. With local minimums on our cos around here, we're going to pick up some local maximums on our sec graph. Okay? And also, just finally, just keep in mind that these guys also intersect at y is equal to 1. So that's something to keep in mind for. And we'll probably revisit that when we look at rational functions later on in this series. Okay? So let's say we want to now sketch these functions. So in this case here, we want to sketch cot 2x plus pi over 6. So we can open up a graphs page. And then to type it in, we're going to use our trig menu. So we press up that submenu, and then we can select our cot function, type in 2x plus pi over 6. So remember to get our pi down the bottom left-hand side here. There's a pi button. We can click that to get our pi over 6. Now we've got a domain restriction where x is between negative pi and pi. So to put in our domain restriction, we need to put in a vertical line given such that symbol. So to get that, control equals brings up this new little submenu, and there's our vertical line there. Right. And then we can go ahead and type in our domain restriction as is, where x is between negative pi and pi. All right, there we go. Now, let's say we're in an exam or potentially any sort of tech active assessment. At the moment, the screen's being occupied up by this sort of label of my function. Ideally, I want to see the function in its full, the graph in its full. So what we can do to get rid of this guy is I've just clicked on it. And it's all highlighted. So what we can kind of do is also like a right click. So it's just like on a computer, we can right click on it, except we can do it on CAS. And to right click on CAS, what we can do is press Control Menu. And I'm just going to hide that label so I can see the graph in its entirety now. So just like a computer, we can right click, and to do so on CAS, that's a Control Menu to bring up a few more options there. So we've got our graph. Maybe now we want to try and find our asymptotes. So there are two ways we can go about doing this. One approach is use the domain command. So if we've never seen this before, we can type in the word domain using our non-QWERTY keyboard. It may take a while, but one option is to type it in. The other option, if you find it a bit cumbersome, is there's this book button here on the right-hand side, the catalog button. If we click that open, it comes up with all the predefined commands in our CAS. So it's all alphabetical. So I want to go to the D section, so I can press on my keyboard D. And I can scroll down and eventually find domain. Okay? And also by using the catalog, it tells us the structure of our syntax. Right? So I need to type in my expression followed by my variable. So we're going to type in our cot, so trig cot 2x plus pi over 6, comma x. And then I can put in my domain restriction just like the solve command or like I just sketched then. So control equals, get my vertical line, and then I can go about using negative pi equal to x. Isn't equal to pi. Right. So what they're telling me is that x can be anything except for these values. So we can kind of think of these as our asymptotes, where x is negative 5 pi over 6, negative 7 pi over 12, negative pi over 3, and so on and so forth. Now, that's one way of doing it. Another way of doing it is to use the solve command. Because at the moment, this is saying x is not equal to. So we could, if we were writing them down on a piece of paper in the exam, we could just simply replace these with equals. But if we want it, I guess, a bit more cleaner in the output, what we could do is change this to solve. And what we're actually going to do is rather than solving the cot function, we can express cot as 1 over 10. Now, to get our asymptotes, that they're going to occur when our tan function hits the x-axis, so when these guys have a y value of 0. So it's going to be undefined when tan is equal to 0. So we can solve tan equal to 0 for the exact same domain. And then now our asymptotes are expressed as equal signs. Now we've got 4 outputs at the moment. So if we look at our graph, we can kind of see that there are 4 asymptotes there, which checks out nicely. Okay, so just like we're doing methods or in Spec, don't forget to look at the graph whenever you can, just to back up your outputs in your CAS. Okay? So another classic exam question that was similar to an exam question from last year. We've got this reciprocal trig function, cosec, and we want to find the implied domain of it. So what we can do is we've just seen the domain command, so we can use that one again. So we can press our catalog button. And there it is straight away, because I've just used it. The domain, and then we can type in our function. So 2 minus 2 times, now, at the moment it says cosec. So we press our trig, and we need to use CSC for cosec. X minus pi over 2. Now, in this question, we aren't given a domain. That's okay. So our output now is in general form. So it's telling you that X cannot be any of these numbers. So even if it's from before, this bold N4, now you may try it on your CAS, you might get an N2, an N3, an N5. Doesn't matter what it is. With this in bold thing here, that's just meaning a natural number. So you can sub in 2, 3, 4, -1, -3 to generate your specific asymptotes. But this is just the equation for the general asymptote. And so X can be any number except for these numbers here. Okay. So inverse trig functions. Now, we may have seen in methods that to find an inverse equation, we need to swap X and Y and solve for Y. So in the context of inverse trig, we can swap around X and Y. And then in order to get Y as a subject, we can take inverse sine of both sides. Now, in exam papers and also other assessments, you may see something called arc sine. So arc sine is just another way of writing inverse sine. And that's similar for cos and tan. You may see arc cos or arc tan written, and they're just equivalent ways of representing inverse cos and inverse tan. So by the end of the year, we need to be comfortable in reading and writing both. So another way to think about it is if we take a step back to Year 9 SOHCAHTOA, Year 9 trig. So if we think about sine, right angle triangle, sine is opposite over hypotenuse. And then if we want to find this angle back in Year 9, we take the inverse sine of opposite over hypotenuse. So in particular, one way you can think about it is the sine function is taking angles and giving you a ratio as an output. It's like sine of pi over 6, sine of pi over 3, sine of pi over 2. Whereas inverse sine is taking a ratio and giving you an angle back. Okay, so it's kind of a geometric way of thinking about inverse trig functions, and also in particular when trying to evaluate inverse sine and also sine functions and trig functions, trying to keep track of what are the actual inputs into those functions. So this sort of way, this Year 9 trig way, can help you identify what the inputs should be. So in terms of the graphs, so just like with any sort of inverse function, there are 2 ways we can think about it. So as we saw before, to find an inverse, we need to swap X and Y. So this sort of green dotted line here is our sine function with the X and Y coordinates. And the inverse sine will appear in blue, where we swap our X's and Y's. And then the other way of thinking about it is we're going to reflect these coordinates in the line y equals x, reflect these graphs in line y equals x. So with sine, it needs to be restricted from -2 pi all the way up to pi. Okay? And remember, as we're going along, our x and y values are swapping. So at the moment, with sine, if x is 0.757, that's going to be the y value of our inverse sine. Okay? So that's one way of keeping track of our inverse trig functions. Okay? And we also need to be mindful of the shape of our functions. So really, we should be really comfortable with our sine function. And then once we chop it at our turning points, then we can reflect in line y equals x to get inverse sine. With cos and inverse cos, it's a bit of a slight trick because it's kind of like the opposite way. So with cos, if we've got a point at 0, 1, our y-intercept, that's now going to become our x-intercept of our arc cos. Right? Then if we go along, the x-intercept of our cos at pi over 2, we're swapping x and y. That's now to become our y-intercept of our inverse cos. And then we go to the next coordinate, our endpoints at pi, pi -1. These guys swap around to become -1 of pi. So I guess really what's happening here is that our cos is starting from left to right, going left to right, whereas arc cos is kind of going right to left in a way in terms of how we map those coordinates. So the main thing we need to be really mindful of is the shape of our inverse cos, and also just keep in mind of the domain and range. So with our cos graph, our domain goes from 0 to pi. So that's going to become now our range of our inverse cos because we're swapping x and y. And then the range of our cos, -1 up to 1, which means now for our inverse cos, we're going left to right from -1 to 1. Right? So swapping x and y, and also we swap the domains and ranges. Now the next graph is going to be a lot going on here. So with our tan graph, to make that an inverse function, we need to restrict that between its two asymptotes, -pi over 2 and pi over 2. All right. So at the moment, we have asymptotes at x equals pi over 2 and -pi over 2. And once again, we're going to reflect these guys in line y equals x. And in doing so, we're going to pick up now horizontal asymptotes at y is equal to pi over 2 and -pi over 2. So our green dotted lines here, x and y swapping. And now when we reflect it in line y equals x, our blue graph, our blue tan graph, is now becoming our brown inverse tan graph, our arc tan graph. Okay? And like before, the domains and ranges are swapping. So before, our range was all real numbers, and that's going to become our domain for our inverse tan. So in summary, this is really important, that our domain for our inverse sine, -1 to 1, range -pi over 2 to pi over 2, inverse cos, and tan. Right, so all that's just swapping around with our domains and ranges from our original functions. Okay. All right, so exam question time. A classic exam question where often in exam 2, we might be asked or be given an inverse trig function, and then we're asked to either find its domain, or one step further is domain and range. So if it's just domain, if we just ask for the maximal domain, we can just simply use the domain commands. But if we ask for the domain and range, because we're doing two operations, it's actually worthwhile defining our function. Okay? So in terms of defining, you may be more comfortable with using the define commands and menu actions define. So we define fx as given the question. Fx is equal to 1 over 3. Times, so to get inverse cos, we're going to use our trig button once again. There's inverse cos. And we type in our function. All right, that's all good. So once again, to find our domain, we can go to the catalog. And because I've used domain before, I can just simply click that. And now, rather than typing in this 1 over 3 inverse cos, because I've defined it as fx, I can now simply type in fx comma x. Okay? And that's going to give me my domain straight away. That's super efficient. Now, in terms of finding the range, so we can be a bit clever here. Because these are inverse functions, they're 1 to 1, what we can simply do is substitute in our endpoints. So if we substitute in -1, all right, there's one y value, and subbing in the next one, there's our other y value. Right? So what we can say is our domain is from -1 to 1, and then our range would be from 0 to pi over 3. Right? Now, often this sort of question takes the form of a multiple choice. So once you find your domain, you might be able to knock off a few options. But then because you've defined your function above, you can then go ahead and check your range super quickly. Right? So the main thing to take away from this is if you're using, in particular, if you're doing two procedures, it is worthwhile and efficient to define your function in doing that. All right. So this sort of question could either be on a methods or a spec paper, sort of style of question. So we've got this function sec squared is equal to pi x over 2. And we want to find the points of intersection between that function and the line y equals equal to 4. Right. So before even doing anything, I'm going to define my function. So I can go menu, actions define, oops, GX. Now, to type in sec squared into the CAS, what we first need to do is type in sec. So I can get that from my trig menu, sec, pi x over 2. Don't forget to put in the times in between pi and x. Right. Now, to get sec squared, once I've done my sec, I can then square all of that now. Okay. So the CAS, unfortunately, doesn't do sec squared, but what it does is it does sec all squared. Right. So that's the way we can type in sec squared into our CAS. All right, now here we go. Now, if we were to do this on paper, what we'd be doing is letting sec squared equal to 4 to solve for our x values and sub them in to find our y values normally, right? We can actually do that on CAS really quickly. I'm actually going to go through a little trick to get our output as coordinates. So what we're going to do is actually, rather than using the solve command to find our x values, we're going to use simultaneous equations, and in particular, systems of equations to do this. And here we go. We've got two equations, two variables, x and y. So just like on paper, we'd be solving sec squared equal to 4 to find our x values. Right? And then once we get our x values, we sub them in to find our y values. So one way you can write that is to say y is equal to g of x. Right? So we can think about it as the top line as solving for our x values, as we do by hand. And then the bottom line is just simply subbing in to find our y values. Now, we do have a domain restriction in our question from 0 to 2. So once again, we need to type in our domain from 0, x to 2. Okay. Now, the benefit of doing this is the output now is pretty much in coordinate form. We're saying that when x is 2 over 3, y is equal to 4. And then when x is 4 over 3, y is equal to 4. So this is a really clean way of getting coordinates just from solving simultaneous equations. Okay. So this sort of technique can be used in both methods and spec. All right. Now, just finally, one other thing that has appeared in past years is often we want to try and sketch an inverse trig graph and label their coordinates. Right. So at the moment, I've got 1 over 3 arc sine root 1 minus x squared. So once again, we need to be comfortable in working with arc sine or inverse sine. So we can go ahead and define this thing. So I'm just working in a calculator page here. So once again, I can define hx as 1 over 3. Now, to get our inverse sine, we use our trig. There it is, just underneath sine. Square root 1 minus x squared. Right. That's defined now. Now, if I want to try and sketch it, I can open up the calculator page. Now, I've already prepared this one earlier. So in my calculator page, because I've already defined hx as my inverse sine, for efficiency, I can just type in h of x. Now, the h is emboldened because I've defined it already on my CAS. And there's our lovely, lovely arc sine graph. Okay, so half the job is done. We've sketched it, but now we want to try to label our coordinates. So we want to label our endpoints with coordinates. So there's two ways we can go about this. On our calculator page, we could either, once again, find the domain of hx, comma x, to find out where those endpoints are, so at -1 and 1. So I could say h of -1 is 0, and h of 1 is 0, just like before when finding the domain range. So I can solve my endpoints, and I know my coordinates will be at -1 and 0. That's algebraically. If you want to work solely in the graphs page, another way you could do this is to go menu, and I'm going to go to geometry because I'm going to put a point on my graph. Okay, so putting a point on my graph. At the moment, obviously this is not, I'll put another one there as well. These are obviously not the endpoints, but what we can do is hover over the X value. I've clicked it, it's currently highlighted, I'll click it again, and now I'm able to modify it. So now I'll type in 1, and it'll take me straight to the endpoint of 1, 0. Likewise, I can hover over the other one, I can click on it, maybe again, right? So now I can now edit it and type in -1 for an X value, and then it'll automatically take me to the Y value of 0. Right, so it's just another way of finding endpoints, and in particular any points, just from the graphs page. So you either do it algebraically on the calculator page or graphically using the graphs page. Okay. Now, I will stress that if you do have any questions, please feel free to ask in the chat. We're kind of at the end of today's webinar. So please, if you have any questions, do ask. And I do sincerely wish you all the best for the year. And hopefully this year's exam will be much easier than last year's exam. But all the best for the rest of the year. And thank you today for joining TI's webinar. And as I said, all the best for the year.